Okay. All right. We'll get started. Okay. Are there any questions so far? Matrices. Okay. We will today do the tutorial on matrices. That's what we'll focus on today, almost entirely. And then tomorrow we'll look at applications of whatever some applications of stuff that we've seen in the first module. Have you looked at the tutorial? Matrices? Not yet. Okay. All right. Yeah. So the first problem is on essentially different ways of doing matrix multiplication. What are the 4 ways of doing matrix multiplication? What are the 4 views? Yeah. Go ahead. Yeah. What is it? See, I don't know if others can hear you. Sorry. Okay. What is the row interpretation? If you have a matrix C equals AB, what is the row interpretation? What is the combination? Sorry. Linear combinations of what? No. Okay. When you say linear combination, no? When you say a sentence involving linear combination, it has to say something like something is a linear combination of something, some other things. You've said linear combination. You've not told me what is a linear combination and of what. Yeah, go ahead. What is it? Okay. Is that the row interpretation? Okay. See, these are all things you should know by now. Okay. Because again, as we go along, right, I might say stuff which involves these ideas and just move on. And if you don't know this already, then it's going to be a problem going forward. We'll look at each one of them. When you have equals equals A. The first thing that we want to do is find out the product, right? And we want to do this using the 4 views. The 4 views are what are they? Inner product view, the column view, the row view, and the outer product. What is the inner product view? Okay. Before that, let's look at this. What is the size of A? What is the size of B? Can we in fact multiply them? That's the first thing we need to check. What is the size of A? Shape of A? Yep. 3/4. Yeah. 4/3. Okay. Can we multiply them? Yes. What will we get if we multiply them? So we're essentially now we need to compute a 3/3 matrix. The inner product view essentially gives you the individual elements of the matrix. It'll give you the ij. You can compute the ij element of the matrix through the inner product view, and the ij element is essentially the element at the ith row and the jth column is obtained using the ith row of A and jth column of B and their inner product. So you take the ith. Remember, this is the representation we're going to use for the ith row of A and the jth column of B. Okay. Now, with that, tell me the individual components that you find out. This is the inner product view. We need to get a 3x3 matrix. Tell me what is C11, C12, C13, etc. Where Cij is given by the inner product of the ith row of A, jth column of B. Maybe I'll do C11. So C11 would be, write it here, but I'll delete it. C11 would be, you take the first row of A and then take its inner product with the first column of B. What is the first row of A? 1, 1, minus 1, 0. The first column of B is 2, 1, 3, 1. And we know how to compute the inner product. What is the inner product? One is it? What is it? 2 plus 3 minus 3 plus 0. Plus 1, sorry, that's wrong. 2, 1 minus 3, 0. Okay, so the first element of the C matrix is 0. What is it? Similarly, tell me what are all the other elements? You sure the second one is 0? This element, C12, that will be the inner product of the first row and the second column. Minus 2. Yeah, okay. I don't know the answer. So you, maybe a couple of you do it and maybe the majority wins. And then when we do the same computation using the other views, all the matrices should match. Minus 2. Okay. Okay. What was the third element? One. Minus 3. Here. Yeah. 2 C21 is minus 3. I'm going to write it. If you're getting a different answer, then you'll have to verify. Minus. Oh, okay. One. Yeah. Minus 1. Plus what? Minus 1. Okay. Plus 4. Okay. Plus 2 is it? Okay. Okay, let's assume that is correct. Yeah. C22 is it? Is minus, is not minus 4. Okay, can somebody verify, please? C22. Second row of A, second column of B, and their inner product. Sir, C22. Times 4, is it? Times 4. Okay, all right. So, you say that is correct. Okay, all right. That's the inner product view. You're taking rows from A, columns from B, and taking their inner products, and that gives you each individual element of the matrix C. Okay? So you need to remember this. When I say inner product view, this is what gives you the individual elements. Next one is the column view. The column view, so the inner product view gives you the individual elements of the matrix. The column view gives the columns of the product matrix C. And the columns of C are the linear combination of columns of A, and the exact mixture for the linear combination is given by the columns of B. Okay? The jth column of C is the linear combination of the columns of A, all of them, how many ever columns you have. And the mixture comes from the jth column of B. That means finally, when the product comes out, the number of columns of your product will be equal to the number of columns of the second matrix, B. In fact, if you look at the matrix multiplication rule, these two need to be common. And what comes out is this times this. For example, if you have two matrices n cross m and m cross p, what comes out, m needs to be common. What comes out is n cross p. Means the number of rows in the product matrix is equal to the number of rows in the first matrix. The number of columns in the product matrix is equal to the number of columns in the second matrix. And essentially the second matrix, so think of it this way, second matrix determines the columns of the product, and the jth column is determined by the jth column of the second matrix. Okay? And the jth column of the second matrix essentially gives you the mixture for the linear combination of the columns of A. And how many columns does A have? Yes, in general, M. And how many rows does B have? M. That means there is one scalar in the jth column of B for each column of A. Okay. Now, that means here in the column view, you get the jth column of C as a linear combination of the individual columns of A, A1, A2, and I'm going to assume there are m columns of A. Each of this is a vector, is a n vector. Okay, and the scalars, right? Those would be your, those would come from the jth column of B. So this will be B1j, B2j, B. Is it clear? Now, let's use that and do the column view. And now we won't compute the individual elements. We will compute the individual columns of C. What is the first column of C? The first column of C is the linear combination of columns of A, and the mixture comes from the first column of B. Let me write down how you would do that. So we would take the columns of A, that would be what? 1, 0, minus 3, 1, 2, 1, minus 1, 2, 1, 0, 1, 3. We want to take the linear combination of these, then minus 2. Yes. If we want to take the linear combination, that means we will multiply each one by a scalar and add all of them together. And where do the scalars come from? We're talking about the first column of C. That means it has to come from the first column of B. And the first column of B is essentially the first one. The first element is 2. Second is 1. Third is 3. This is 1. And then we simply then add all of these together. And that will give me 2, 0, minus 6, plus 1 to 1 plus minus 3 minus 6 3 1 0 1 3. What will that give me? 0 2 minus 4 plus 1 3 minus 5 minus 2 plus 1. There. So I write it down here. So this will be 0 minus 3 1. They match. So looks like our computations are okay. Or at least we made the same mistake in both of them. Now you tell me what will be the second column of. Don't just tell me the column from the first computation. Please do the computation yourself and verify for yourself that it in fact matches. Yep. Second, what is the second column? Minus 2 minus 4. That's okay. And third one. Third also matches. Third one is actually easy. You simply add all the columns. That's it. One. First one is 1. Second one is 1. That's it. That's okay. Almost fine. Okay. Now the row view is kind of complement of the column view. The row view gives you how to compute the rows of the product. And how many rows will we have in C? The product. There will be the number of rows of A, number of rows of B. It will be the number of rows of A. That means the rows are determined by the rows of A. Okay? And the rows of A will determine the mixture for the linear combination of the rows of B. So the rows of C are the linear combination of rows of B, and the mixture comes from the rows of A. So the jth row of C, remember this is the notation we are using for the jth row. will be a linear combination of the rows of B, right? B1 tilde transpose plus B2 tilde transpose. And how many rows do we have in B? Oh, well, in this case, M. Okay. And where do the the scalars come from? For the jth row of C? No, jth row of C. That means it will be the jth row of A. So the first element of the jth row of A will be AJ1, AJ2, AJ. Is that clear? Okay. Now you can tell me for the computation for the row view. I won't do the rows. You can do the rows and tell. The way you do that is you take the first row of C, you take the first row of B, multiply it by 1, multiply the second row by 1, third row by -1, fourth row by 0, and add them all together to get the first row of C. So, okay, so you should get okay. Now we'll move on to the last one. So here, see if you notice one thing, right? How many plus signs did we have here in the column view? Assuming A is n cross M and B is n cross P. Or how many elements are we adding? 1, 2, M. So we're adding M elements here. How many elements are we adding here? M. In the inner product here, how many scalars do you eventually add when you multiply the individual elements? There will be M. Okay. So here you're adding M scalars, you're adding M columns, M rows. In the outer product view, you will essentially be adding n cross P matrices. Okay. So C, your entire matrix will be, I'm going to call it, they don't have a symbol, but I'm going to call it C cap 1, C cap 2. You're going to be adding M matrices, where each matrix, the ith matrix is given by the outer product of the ith column of A with the ith row of B. And you can verify that this will in fact give you a n cross P matrix. Assuming A is n cross M and B is n cross P. So let's do the outer product. Let's compute each of those matrices first. Okay, what will be C1 cap? How many outer product matrices will we have in this case? In this example, 4. We will have m things that we will add, so there must be 4. Okay. So what is the first one? First one is given by, you take the first column of A, first row of B, and this should give you the first of the outer product matrices. This will be what? 1, 0, minus 3, multiplied by 2, 1, 1. What will you get? Okay, there is often a simpler way. You don't have to compute each individual element. You can think of the outer product in 2 ways. The columns of, well, it's the same as matrix multiplication, right? You're multiplying 2 matrices. What can you say about the columns of the product? The columns of the product will be linear combinations of the columns of this matrix, and the mixture come from this. There is only one column in the first matrix. That means the columns of the product would simply be scaled versions of that one column. Okay? That means, and how much you scale is given by the second matrix. So the first column will be 2 times this column, second one will be 1 times this column, third one will be 1 times. You can also compute the rows. The rows of the resulting matrix will simply be scaled versions of this one single row. That means the first row will be the row, second row will be 0 because this is 0, and third row will be minus 3 times this row. So this will be 2, 0, minus 6. This will be 1, 0, minus 3. And you can verify that. The row and column view and the inner product view actually hold for this. What about C2 cap? The second column of A, the second row of B, and their outer product. Second column is 1, 2, 1. Second row is 1 minus 1, 1. What does that be? And then you can tell me what is C3 cap and C4 cap. This will be what? 1, 2, 1, minus 1, minus 2, minus 1, 1, 2, 1. What about C3 cap? Minus 3, okay? Is that okay? So you're taking this, and this. What about the second one? No, it will be minus 2, minus 4, 2. Here. This with this. That means the first column will be 3 times this, second column will be 2 times this, third column will be 1 times this. If you're not sure, just write it down. If you can't do it in your head. Yeah. Zero, 1, 3. Yep. Okay. Now you simply add C1 cap, C2 cap, C3 cap, and C4 cap, and that will be your final matrix. Yeah. So you essentially add Please, that will be your C. 0 minus 2, 0. 2 minus 1. 0, 2 minus 4 minus 3. 0 minus 2 minus 6 minus 4. 0, 2, 0, 1. Minus 6 minus 5 minus 2 plus 1. Minus 3 minus 4 minus 2 plus 4. Minus 3 minus 2 minus 1. Is that correct? Yeah. Okay. There. So those are the 4 views. Okay? I hope that sticks now. And I hope that you will remember the 4 views and how to compute them. So that is the first problem. At least first part of the first problem. Now look at the second one. So let's say we've computed the product of A and B and obtained the matrix C. Now, if somebody comes and says, okay, well, there is a mistake in B and that B is B23, that means the second row, third column element of the B matrix is actually 0. Now the question is, that is the new information. The question is, can you compute C without having to? Okay. Now, to compute C, do you have to now recompute the whole matrix again, or is it, or do we only have to compute specific parts of the product matrix C? Okay, what parts? It's correct. You don't have to compute the whole thing again. What parts will you need to update now? Okay, if you tell me what parts, you'll have to explain also why that part. Okay. The B23 element has changed. Now, what all do we need to change in the C matrix? Do we have to change the first element, second element, or 1, 1, C11, C1, C12, or do we change the first column, second column, third column, second row, third row, fourth row, etc.? Or how do you go about? It's maybe intuitively clear that you don't have to compute the whole matrix again. Is that intuitively clear or no? Or does it feel like no, you have to compute the whole thing because we don't know how B23 impacts the elements of C? So I hope it's intuitively clear that you don't have to compute the whole thing. Okay. Now, how do we figure out what parts of C do we have to now recompute? Even without going into the details, what all would you have to recompute in a situation like this? Exactly. Whatever operation involves that particular element, I only have to compute those. That's correct. That's the first step. Now, using that logic, how do we figure out what aspects of C are impacted by the element B23? Exactly. So, the element B23 is in the which row of B? It's in the second row in the third column. Okay. How does the second row or the third column of B impact my C? Does the second row, let's look at the column. Does the second column of B impact the first column of C? Sorry, second row? Yeah, but does the second row of B impact the first row of C? No. Okay. Why? Yeah. Are you sure it does not impact? Does the second row of B not impact the first row of C? How do you compute the first row of C? Go to the row view. Look at the row view. The jth row includes all the rows. That means if I change one row in B, I am potentially impacting all the rows in C, right? Okay, all right. So it looks like I might have to recompute everything. Right? Okay, that's what the row view says. What about the column view? How does the element that changed is in the third column of B. How does the third column of B impact the columns of C? Sorry? Or what does the third column of B impact all the columns of C? Go back to what the column view says. Yeah, what is it? Exactly. It will only impact the third column of C. Yes. In fact, the row view and the column view are not saying two different things. They're actually saying the same thing. If it impacts a column, that means it impacts all the rows. Right? So the row view is saying every row is affected, okay, but only the third column is affected. And so we don't have to recompute everything. Okay, now what would you do? How do you recompute? So you only have to recompute the third column of C. The computation you will have to do is essentially pick this as the new column of B and then recompute the final column of C, the third column of C. So we are essentially saying instead of adding all the columns, only add the first, third, and the fourth columns of A to get the third column of C. So that will essentially be what? So add all the columns except the third one. No, it will be 2, 3, 1. The third column of C. So 1 plus 1 plus 0, 0 plus 2 plus 1, minus 3 plus 1 plus 3. 2, 3, 1. A similar question. If we increase the value of the elements of the third column of A, okay, by 1, how do you recompute the new C without, of course, performing the entire matrix multiplication operation again? The third column of A has been increased. All the elements of the third column of A are incremented by 1. So the only thing that's changed, the things that have changed is an entire column of A. Use the same logic and tell me how we can recompute C. Okay. I don't know. You argue and tell me if the row view is the correct view or some other view is the correct approach here. Explain. You should not guess. Okay, column view. Why the column view? And what would you do? Okay. You'll have to be louder, Adesh. Sorry, I don't hear that well, and the fans are loud as well. A matrix, yes. So you said we can use a column view to figure out how to recompute, right? You tell me what you do exactly. Yeah, maybe the column view is correct, but explain it to me as to what the new computation would be without having to redo the whole matrix again. In the column view, we're computing the columns of C using the columns of A, taking their linear combination, and the mixture comes from the corresponding column of B. Okay. A. Okay. The columns of C are a linear combination of columns of A. If you change the column of one column of A, right, won't that impact all the columns of C? Here, jth column depends on the first column, second column, nth column. So every column depends on every column. Every column of C depends on every column of A. Okay, if it's a row view, tell me, okay, what do we do? No, you have to be careful. It's not the entire matrix. If it's a row view, we are only talking about the rows of C. Where the rows of C are a linear combination of rows of B, and the mixture is given by a corresponding row of A. Okay, all right. Okay, I'm going to leave this for you guys to solve, and you can tell me tomorrow. Yeah, I don't want to. I don't want to give you the answer and deprive you of the joy of figuring it out. Okay, all right. You can do it yourself. Okay, all right. Let's look at the fourth one. I think you understand what needs to be done. Now we do something different. The one vector, you remember, it's a vector of all ones. We take in the transport, that means it's a one row now. Okay, it's not a one column, it's a one row. That's inserted after the second row of A. That means A is changed now. A is not the same matrix. A is now 1, 0, first row, second row. And after that, we've inserted 1, 1, 1, 1. Okay. So the question is, how do we recompute? The new matrix C. Oh, sorry, we've also, hold on. If we insert a new row in A, after the second row features, that's correct. Yeah. Now the question is, do we have to now recompute? So two things will change, right? The size of A has changed. That means the new C, what will be the size of new C? Earlier it was, in fact, if I insert a new row in A, can I even multiply A and B anymore? You can't, is it? What is the new shape of A? Or what is the shape of B? Can you multiply or no? We can still multiply. It's just now C is 4 cross 3 matrix. Looks like the shape of the matrix itself has changed. Now the question is, do we have to now recompute all those well, we computed 9 elements from before. So we have to recompute the whole thing again. Okay? That's the question. Again, I won't do it. It's a good opportunity to really dig deep into your understanding of the 4 views. Okay? I'll add one more, and then I'll leave it there. E. I insert one column after the third column of A. Okay, and I insert one row after the third row of B. Okay. Now, what is the shape of the new C? In fact, can I first multiply? Yeah. What is the shape of new C? What is the shape? Sorry. What is the new shape of new A? Five, no? There is one here, one more column here. What will be this? What will be the shape of this? So shape has not changed. Now the question is, would you have to recompute the entire matrix again? Okay. All right. I'll leave it at that. We'll move on to another problem. Second one, let's say we have a huge matrix which has 1,000,000 rows and 5 columns. And for some strange reason, we need to compute this matrix. A transpose A, A transpose. Yeah. No. This is a 2 cross 1 matrix. This is a 1 cross 4 matrix. So you'll get 2 cross 4. Can you actually compute this product? That's the first question. This is the A. This is the A. I want to compute this. The first question would be, well, you can't multiply any matrices you want, any 2 matrices you want. Can we multiply this? You tell me that first. Just take 2 matrices at a time and then see if they can be multiplied. That's all. You can either start off with this and then check product with this, or you start off with these two and then check this. You can't. Why? Can you multiply A? So let's check it step by step, right? Okay. You say you can't know. Where does it fail? First, okay, let's take the first two. Can you do A transpose A? Just check the size, that's all. Check if the shapes are compatible, that's all. What is the shape of A transpose A? Or A transpose? What is the shape of A? Are they compatible for matrix multiplication? Sorry, it's not, no? So if it's square, so what is the question? Let me listen to your question first. A is not a square matrix. A is 1,000,000 cross 5. Can you do A transpose A? That's the question first. Yeah, you can. Why is everybody so confused? You should have told me this immediately. This is 10 power 6 into 5. This is 5 into 10 power 6. It's fine. These are compatible. What will be the size of the resulting matrix? 5 cross 5. Okay. So then you take this and you multiply it with this. Can it be done? Yes, 5 cross 5 into 5 cross million. So that's fine. So you can do you can also check it the other way around. Okay. Now the question is, well, you have to multiply three matrices. There are two ways you can do this multiplication. I've written it down. I can either multiply these two first and then multiply the result with this, or I can multiply these two first and then multiply the result with this. Which one is better if you want to save space when you're doing the computation? Save space in the sense you want to make sure you don't have to keep track of too many numbers at the same time to be able to compute this. Okay, if you see the second one, explain it to me why. Okay, what does it, correct, A into A transpose, what does that give me? What is the shape of the matrix it gives me? 10 power 6 into 10 power 6, okay. It's good. How many numbers are there in this matrix? How many elements does this matrix have? How many elements does a 2 cross 3 matrix have? 6. How many does this have? Okay, fine. And then you have to multiply this with this has 5 million. And then you have to keep track of 10 power 12 elements and then multiply it with this. That's the A matrix. Okay. What is your other option? The other option is the first one. What about the first one? If you do A transpose A first, what do you get? 5 cross 5, right? This has 25 elements. And this you have to multiply by a matrix with. Which one is better? The first one, right? Because remember, whatever is in the parenthesis, right? That's the intermediate result. That's not the result you're interested in, right? So it's better to do A transpose A first and then multiplying by A transpose than do A transpose and then multiplying that, post multiplying or pre-multiplying that by A transpose. Because in the second case, you'd have to store a huge matrix, 10 power million cross million rows and million columns. Whereas in the second one, you only, whereas in this approach, you only have to store a 5 cross 3. Will this change if the order was different? If it was not a million cross 5 matrix, but it was a 5 cross million matrix, will the order be the same, or will your answer be different now? If instead of being million cross 5, what if this was 5 cross million? Well, if it's 5 cross million, you still have to verify if you can still do A transpose A transpose. Can you still multiply the 3 matrices? Yeah. The resulting matrix will be 10 power 6 into, okay, 10 power 6 cross 5. Okay, so you can multiply. What order should you multiply them in? Should you do A transpose A first and then post multiplied by A transpose, the first approach, or the second approach? So the second approach is better in this, right? Okay. Yeah. So the point I was trying to make is, if you want to make your computations efficient, the order in which you multiply, if you have highly rectangular matrices like this, in the order in which you do the operation will really make a huge difference. Okay? What if A was really square matrix. Can you still multiply? And what order is better? Oh, what do you mean by saying? It doesn't matter. You're saying it doesn't matter what order you multiply with. Exactly. If it's square, then you really don't get any. You don't get free lunch. It doesn't matter what order you do it in. You have to confront a 10 power 6 into 10 power 6 matrix anyway in your computation. We've not listed orthogonal matrices. Yeah, we skip that. Let's do this one. I will leave the other ones for you to try. We won't come back to this tutorial again. But you must really try them. And if you get stuck, just come and talk to us. If you're not sure, come and talk to us. We talked about symmetric matrices, right? What is a symmetric matrix? No, symmetric matrix. No, that's a triangular matrix where the elements below the main diagonal or above the main diagonal are zero. Well, symmetric matrices are matrices where A transpose equals A. That's all. Okay. If A transpose equals A, then A must be square. Right? It cannot be rectangular. Right? Because the shape of the matrix will change if you take the transpose operation. There is no comparison between two matrices with different shapes. You can only compare matrices with the same shape. So symmetric matrices are matrices where there are square and A transpose and A are the same matrix. That essentially means you have the diagonal elements. The elements above and below the diagonal are essentially mirror images of each other. Okay? Or another way to say that is Aij will be equal to Aji. You can verify that. Okay? If A transpose A equals A, that implies Aij equals Aji. Because when you take the transpose, you're converting Aij to Aji. There is another version of this. It's called a skew symmetric. Symmetric matrices are very important because we come across them all the time. And so are skew symmetric matrices. And skew symmetric matrices are simply this. A transpose is not equal to A, but A transpose equals minus A. And when you take this transpose operation, the new matrix looks like as if it's minus of A. So if those are skew symmetric matrices, the question says, or the question, or this property or this problem says, for skew symmetric matrices, the diagonal elements have to be zero. Question is why? If A transpose equals minus A. Yes. So when you take the transpose operation, right, of a square matrix, the diagonal elements will not change positions. The diagonal elements will all be where they were before. Okay? So let's do an example. If I take the transpose of this, what will I get? 2, 4, 0, 3. Is this a symmetric matrix? It is. So transpose of this equals this, right? This is okay. Let's assume this is A. I'll remove the transpose. A transpose is 2, 4, 0, 3. Is A a symmetric matrix? Well, if A was a symmetric matrix, A should be equal to A transpose. We simply compare the individual elements. 2 is equal to 2, fine. But 0 is not equal to 4. That means these are not the same. So this is not a symmetric matrix. What about this? What is this? This will be 2, 4, Is this a symmetric matrix? It is. So as I said, the elements above and below the main diagonal are the same. If you want an example of a 3 cross 3 matrix, then you simply do this 1, 4, 5. This will be 1, 4, 5. You can verify that this is in fact a symmetric matrix. Now, if you look at the main diagonal, 1, 4, 5, 1, 4, 5. If you take the transpose, A transpose will be equal to A. So that's what symmetric matrices look like. And when you do transpose operation, the ijth element of A will become the jith element. And I will essentially be II. Because if you're switching I and J, the ith element, that means the diagonal element will be the diagonal element. And that will not change positions. And that you can verify here. 2, 1, 2, 1. Whether you're symmetric or not, the diagonal elements don't change positions. And they remain the same. But if you have a skew symmetric matrix, where A transpose is minus A, is this a skew symmetric matrix? This is A. A transpose will be 0. No, A transpose. Columns become row. First column becomes the first row. What is this equal? Minus of A. Right? If we take the negation of all this, this will become plus 3, this will become minus 3. The diagonal elements are 0. Okay? And because when you take the transpose operation, the diagonal elements don't change, the only way some element of A matrix will be equal to minus of the transpose of the corresponding element in A transpose would be if the diagonal elements are all 0. So in fact, this is true. The reason it is true is because when you take the transpose operation, the diagonal elements don't change. So if A transpose equals minus A, the only possible value the diagonal elements can take without changing their value when you do a negation operation is if it's 0. If it was 1, it's not true anymore. So this will be 1, 3 minus. This is not equal to minus A. Minus A would be minus 1, 3, minus 3, 1, minus 1. And that is not A transpose. Okay, all right, we'll stop here for today. And then we'll move on to applications. The first module tomorrow. And if there is time left tomorrow, then maybe we'll come back and do 1 or 2 things again. Thank you.